All right, how's it going, everybody? We are here on January 22nd, making our video for section 1.5. We're going to discuss existence and uniqueness today. And just really briefly, just since I said the section number, I did in my last video say that this section was 1.4, existence and uniqueness. Section 1.4 in our textbook is our first look at numerical approximations to solutions to differential equations. But remember that we're going to hold off on that one and gather up all of our numerical stuff into one little unit. Section 1.4 and section 2.4 are both going to cover these numerical topics. We're going to kind of skip them both in order, but then hit them both at the end of chapter 2, kind of collecting all that stuff together rather than like doing a little bit now and a little bit later. So I just had a wrong section number, but correct section title in the previous video. So in any event, today is section 1.5, existence and uniqueness. Next week, we'll pick up with section 1.6, which will be equilibria and phase lines, which is going to be like an improvement to the graphical stuff that we've been doing. So today is going to be a very graphical day. It's going to be very much a concept day. It's very much less a doing day and much more of a thinking day right here. So a little bit different than I think a typical like day of calculus goes for today right here. Today we're really going to discuss two super important theorems and how we are going to sort of intuitively be applying these things. And it's going to be really important for us for like a huge part of the semester. This will definitely be something that's going to follow us around here for kind of all semester here, existence and uniqueness. So let's go. So what do we even mean? What does existence and uniqueness mean like as ideas here? In general, we're saying given a differential equation, how do you even know that it has a solution? And as we kind of talked about last time, maybe it has a solution, but like there's no like closed form for it. We've already seen some that have implicit solutions, but not explicit solutions. How do we even know that there does exist a solution to a differential equation? And even more than that, if I were to then also, so that's just a general solution. If I were to give you initial conditions, how do we know that there's only one particular solution associated with a certain initial condition and a differential equation? Maybe there are multiple different curves that we could draw that all go through the same initial condition that all satisfy a differential equation. Is that possible? And that's the topic of today. So how do you know that a solution exists? And if there is a solution, which you are picturing graphically as a curve going through a properly or not properly chosen, an arbitrarily chosen initial condition, how do you know that there's only one if you do know that there's any at all? Maybe there's multiple possibilities here. Maybe we've only been finding a small subset of the solutions that exist so far this semester. That's what we're going to talk about. So what today is not about is finding solutions. We will solve a couple differential equations today, but only to like kind of highlight some important things that are going to happen here. Today's not about solving differential equations, but it's about confirming or denying the existence of solutions, saying I know it's going to have solutions, I know it's not going to have solutions, I know it has only one solution, I know it has more than one particular solution, stuff like that. So what I want to first hit you with is the idea that you have discussed existence and uniqueness theorems before. You just didn't really know it, or I should say, nobody cares when I teach this in algebra class. This is just one of those things I don't know how to get anybody jazzed up about when it's discussed out there. And this typically comes up in algebra. It more formally comes up in Calc 1, and normally people there are equivalently not excited about it right here. So let's talk about the algebraic existence theorem that you do know. And right now, you should be thinking to yourself, what existence theorems do I know? And I'm sure that you're not coming up with any right now, or I'm assuming. And so let's do this guy right here. So consider this quadratic. Does it have real solutions? How do you know? Well, obviously, I'm thinking that a thing that you could think to yourself is like we could try and factor this, or we could try to complete the square, or we could use the quadratic formula and stuff. But I just want to use, I'm not interested in finding the solutions. I'm interested in knowing if it has a real solution or not, right? Not complex solutions out there. And I think that this is something that you have seen before. I just got to remind you. So what I'm going to do is I'm just going to think about some x expressions right here. And I guess what I should be saying right here, I don't know. I'm going to write this as, I'm going to just rephrase this as an equation instead of a, or like a function instead of an equation right there, like a y equals equation right there. So what I'm going to do is I'm going to say, well, I could go ahead and I could plug in x equals 0. And if I plug in x equals 0, what I can see that I'm going to get from this guy is y equals 5. And maybe another thing I could do is I could ask myself what's going on at some other location, like 1. And if I plug in 1 into this equation, 2 minus 10 is negative 8, plus 5 is negative 3. What did that tell you? What we know here is that the intermediate value theorem that is going to insist that there's got to be a root here. And I know that there's a root between 0 and 1, a real solution. The reason I know this is because this says that since y is continuous, and let's see, maybe I'll just phrase this as y of 0 equals 5 and y of 1 equals negative 3, there must be a solution in the interval 0 to 1, right? Somewhere between 0 and 1, we must be getting a y value of 0 because we have y values that are positive, y values are negative, and I know that quadratics are always continuous, right? So the intermediate value theorem is an existence theorem. The intermediate value theorem does not tell you where to find, well, we found a region in which the root might live. It doesn't find the root for you. It just tells you, yep, I am positive that there's going to be one. And that's all that it says. It stops right there. And I feel like that feels lame back when you were in a math class where you actually expected to be able to find solutions to things all the time. But the kind of like the guiding principle of this entire class is you probably can't solve the equation. You probably can't solve the differential equation. All the ones that we're going to look at this semester are like so special just to be able to be solved so that we can analyze some early easy stuff here. But broadly speaking, you shouldn't expect to be able to solve differential equations. And so therefore it matters more that you can even make statements like, well, is there a solution, whether I can solve for it or not? And so the intermediate value theorem here is a very good algebraic example that is doing for us what we want to be doing in a now calculus setting right here. So this is like my analogy for the day is the intermediate value theorem. It is an existence theorem from algebra class that tells you about existence of roots of continuous functions. We would like to sort of extend that idea now to solutions of differential equations instead. And one of the things that you're seeing here is that one of the keys to the intermediate value theorem, like the one thing we have to know, is that the function is continuous over a closed interval, or over the entire real number line right there. Since this function was continuous, the IVT applied, and we were able to claim we know for a fact that there's a solution between 0 and 1. So continuity mattered right there. Otherwise, we could have just had a discontinuous function that just jumped over the axis. Right? So let's go ahead and state this. We're going to get two essential theorems today, the existence theorem and the uniqueness theorem. We're going to see that they're almost the exact same theorem. The uniqueness theorem just has one additional little piece to it right here. And the reason I've been forcibly not scrolling my screen down a little more is because this theorem, there we go. There's the word at the bottom that I'm kind of trying to say there. It's a bit of a tough read, but also you need to learn how to read math. So let's like read this together right here. So the existence theorem, given a general differential equation and a general initial condition. So this is overall an initial value problem. It's not just a differential equation. It's a differential equation with a initial condition. Right? If our function on the right-hand side of our differential equation is continuous on a rectangle. Now here's my our first slightly difficult statement right here. And by the way, I actually have to modify a symbol here. What this is saying is that the rectangle right here is the rectangle AB crossed with CD. Right? So what I'm picturing right here is I'm picturing that out there in the plane, that there is some AB and that there is some CD, and therefore the rectangle that those guys collectively make as a cross of two areas is going to be this region that we're looking at right there. There's AB cross CD right there. So what we're saying is if the points that we're considering, the TY points that we're claiming that this is continuous over, so this is our region of continuity. I'm saying I'm positive that this function is continuous at least within this rectangle, which is contained within R2, right? A real number line cross a real number line that just has two-dimensional space. And by the way, my little technicality, just because I couldn't get this symbol to happen in Microsoft Word, this symbol, it means it's a proper subset of R2, meaning it is like it can't be all of R2, but it can be right here. We can say that we're continuous over the entire two-dimensional plane out there. So there really should be like a line underneath that. That's sort of like our greater than or equal to. It's like contained by or is the same as all of R2. And if our initial condition is also an element of the rectangle in space, right? So also notice I just glossed over this symbol right here. That little weird E symbol says an element of. The other tough thing about reading some of these math notation things here, and again, I'm kind of expecting that there's some math notation that's new to some of you guys here. I don't know. Learn to read math notation here. I'm doing this. I could have written all this out in words, and I chose not to on purpose so that you can get used to seeing this a little bit right here. One of the slightly difficult things is that this E right here is actually a totally different E than this E right here. This means is an element of. This is suggesting containment. That says that this point is one object in the infinite number of points contained in this rectangle. Then, oh man, we even got a third E going on here. Then there exists some function y of t and some epsilon greater than 0, such that that function y is defined in some region about that t location, and that y of t is the solution to the initial value problem. And yikes is an appropriate word at the end. I do want to write some of these guys right here. So this would say x is an element of x, right? So that might be an object in a set. That's this element usage right here. The next E that we end up seeing is the backwards E. Backwards E says there exists. So there exists a function y of t and an epsilon greater than 0. You guys have seen epsilon in your Calc 1 and perhaps Calc 2, Calc 3 classes. Epsilon is just a constant, but it's very often meaning to indicate potentially a very, very small constant out there, but we're not too worried about the size. It's just a positive number out there. So 3 different E's that are maybe things that you need to sort of have seen for the first time and remind yourself of. But the bottom line is like, holy cow, this is a tough thing to read through right here. So what we want to do is kind of simplify down what we just saw for ourselves right here. All this is, I think the big takeaway is this. All right, so my a little bit easier version down here in English. If f of ty, our differential equation expression on the other side of the equal sign, is a continuous function, then a solution to the initial value problem does exist. The only thing that we got to watch out for, though, is that this function might exist in a smaller region than the overall function was continuous over, right? So the solution might exist over a smaller subdomain than over which the entire function was actually continuous, and the continuity was a requirement there. So what we're going to do is we're going to look at an example that's going to very explicitly show this, oh, potentially it's over a smaller subdomain issue right here, and see why that is exactly, like I said, an issue right there. So looking at our first example right here, before we go on to that uniqueness theorem right there, what I want to say is f of ty equals 1 plus y squared is continuous. So solution exists. All right, so one thing I know is whether I can solve this or not, I know that there is a solution to this initial value problem, and the way that I know that is simply because the differential equation function 1 plus y squared is a continuous function. Only requirement. That's awesome. Now the other thing that I can see here is this has a domain of all real numbers. Right? There's no issues with plugging in any value of y, any value of t into this that you want. No issues right there. We can plug in literally any value that we want. Let's go ahead and solve this differential equation now and see what we end up with for our solutions over here. This looks separable since there's no t. This is what we call an autonomous differential equation. That's a very, very important class of differential equations here. No time dependence. It's autonomous. It is not dependent on time. So I'm going to do my algebra here. I'm going to apply that integral to both sides. Stop for a second and remind yourself that you're supposed to know this one. This is just the integral of 1. The integral of 1 is t, and we get our constants grouped together here. What we want to know is the solution y. So I'm going to apply tangent to both sides. And now that we've found our, okay, I should have given myself a little more room here. I'm going to have to bump all this, aren't I? I am. So now let's apply our initial condition here. We've got that y of 0 equals 0 says to me 0 equals tangent of c, and therefore c must be equal to what makes tangent 0? That's all the places where sine is equal to 0. So that should be at like pi k. So that's really just saying that like 0 is maybe an acceptable value of c, or like a trivial shift. We know that tangent's a repeating function, and this is just saying right here that, like, in a sense, 0 is an acceptable value of c. So c equals 0. All right. If we're going through 0, 0, then I don't want to shift over to one of those other groupings that's over there. So it looks like we just determined that our solution should be looking something like. Now I know what the graph of tangent looks like, and this is really important here. I know that there should be lots of these solutions that are out there because we're going to get all these tangent graphs. But importantly, our particular solution right here only lives in the interval from pi halves to pi halves. It is discontinuous outside of that. Our particular solution, the one that goes through y of 0 equals 0, that's right there. This is our particular solution. So kind of our takeaway here is that F's domain is all real numbers. But our particular solution has a domain of negative pi halves to pi halves non-inclusive, right? So this is saying we were guaranteed that we were going to get a solution to the initial value problem because 1 plus y squared is a continuous function, but we're not guaranteed that the domain of our solution, of our particular solution, is going to be as much as the domain of the original problem. Now, does this matter to you? Well, yeah, it does, because the entire purpose of this class is to be able to model real-world scenarios. What we're saying right now to ourselves is that this real-world scenario has no description beyond time pi halves. Well, is this really a good model then? And the answer is probably not. If this is trying to be modeling some real-world scenario, this model cannot make any description of what's going to happen beyond, 1.57 units of time off into the future. Pi halves units of time right there. So this seems like this probably isn't a very good model for describing real-world things, since it can't make predictions beyond pi halves units of time off into the future. Right, so I think the book says something like this is a red flag for real world modeling right there. If your model has solutions that don't exist for all the times that you might want to make predictions, then that's probably not a very good model right there. So in general, there's nothing like inherently wrong with this differential equation, but if you're trying to use it to describe a real world process, it's probably not going to be very good because all the particular solutions only exist for a 1 pi interval width of time. Before they tend off towards infinity, diverge, sort of break in a sense right there. And if you are confident that this is an appropriate real world model, you should be super concerned at this point then, because it seems like something is tending off to infinity in finite time. That's concerning. But then again, that just leads me to believe this probably isn't a good real world model. So in any event, this is sort of our good example of seeing what do we really mean. So very, very difficult paragraph to state the theorem. Much, much easier English rephrasing of the theorem, but still saying like, well, why would we get a smaller subdomain? And that's just going to be because those are the functions that are going to pop out from integration right here. It might be that we introduce some discontinuity, some subintervals only over which the particular solution exists, much narrower than the original function's domain right there. So there we go. There's our first example. And what I want to say about this before I guess we move on is the book even, aside from me not stating it, the book also does not state a proof of the existence theorem, I believe, unless they updated it in the 4th edition out there. I think that this proof is. I trust that you're all going to go to grad school and learn your proofs of your existence and uniqueness theorems right here. I think, in a sense, that I like the analogy with the intermediate value theorem. I think it's very easy for me to understand why the intermediate value theorem absolutely requires continuity. And so I think that that makes me feel better about the intuition behind this existence theorem right here. But it's always going to be a little bit tougher when we bring in calculus and needing to have derivatives be continuous and stuff like that. Right? So now let's talk uniqueness theorem. So now we're saying if we can find a solution to an intermediate value problem, how do we know that there's not another one, right? And here is my potential graph for you right here, right? If you are given some initial condition that sits out there in space like that, maybe you come along and you find some solution curve that looks like this. How do you know that I'm not going to find a solution curve that looks like this and that they're both going to be right? Is it possible for that to happen or not? That's what uniqueness means. If we find a solution, is it the only one? That's what uniqueness means. There is a unique solution for each initial condition, one and only one possible solution at that initial condition. So I should just this is like what gets my question mark right here. So let's state our uniqueness theorem. And what we're going to see is it is phrased up very, very similarly to the existence theorem. However, and before I even scroll down, I want to kind of just state this general proving strategy to you. It's very, very common in every single branch of math. There are existence and uniqueness theorems all over the place. We always are interested in classifying entire groups of functions and saying all these functions are guaranteed to have solutions. All these functions are known to have unique solutions, blah, blah. Those are really powerful statements to be able to make about entire categories of functions. So these are not like unique proofs right here. No pun intended right there. There's not something super special about these. These exist all over the mathematical realm out there. So there's lots of uniqueness proofs. A very typical strategy in proving that something is unique is to suggest that there are two possible solutions, as I've drawn in the picture right here, but then use the cleverness of the proof exists in showing that those two suggested solutions are actually the same thing as each other, saying, oh, I thought I had two things, but it turns out they're actually equal. They're the same thing. So there's not actually two different solutions, right? Saying that if there are two solutions, they must be the same thing. That's a proof of uniqueness right there. And that's how this one is exactly phrased, right? There's one extra important part of this one, though, and I have highlighted it. So given a differential equation and a generic initial condition, the requirement of the uniqueness theorem is that if f of ty and the partial derivative of f with respect to y are continuous. So the only big step up for this one is the continuity requirement applies to not only the differential equations expression, but also to its partial derivative with respect to y. I'll talk about the partial derivative in 1 second here. If those are continuous on a similarly defined rectangle, and if our initial condition lives within that rectangle, and here's what I just described to you about the general structure of uniqueness theorems. And if there are two equations, y1 and y2, that are both solutions to the initial value problem, then it must be that those two solutions are equal to each other. So that's a typical formation of a uniqueness theorem, is to suggest that there are two solutions, and then to verify that it must be the case that those two solutions are equivalent to each other, are equal to each other, saying, so no, there really was only one that's out there. So the one thing that we have to grapple with on this one is we need to be able to verify that not only is the original function going to be continuous, but that also its partial derivative with respect to y is continuous. Right? So let me talk through that a little bit right here. I'm just going to bump that down. Partial derivatives. One thing that I know, so let me just kind of talk about like our curriculum here. Everybody takes Calc 1, everybody takes Calc 2. From Calc 2, you are then able to take both Calc 3 and differential equations. Calc 2 is a prerequisite separately for both. So what that means is I know that some of you that are taking this class have taken Calc 3, where partial derivatives are defined. Some of you taking this class have not taken Calc 3, coming here directly from Calc 2. Completely appropriate. It turns out one partial derivative pops up in here. I'm going to show you a partial derivative here real quick. So let's suggest an f function. I'm going to do f of t y equals t minus y squared t plus t squared y right there. So suppose this is some differential equation that we've been given. When we talk about partial derivatives with respect to some variable, what that means is that even though there technically might be some we're sort of treating each of these as their own independent variable. So if I were to take the partial of f with respect to t, what that says is assume y is just some constant. Don't think of y as a variable anymore. Just take the derivative with respect to t, assuming it's the only true variable. So that would give me 1 minus y squared plus 2ty. On the other hand, if we took the partial of f with respect to y, this says assume t is a constant and just compute this derivative as if y was the only variable. That means to me t is a constant, so that goes to 0. I would get a negative 2yt, and I would get a plus t squared there. So when we do partial derivatives say assume that this is the only thing that is changing, the only variable that's changing, therefore all other variables are held constant. The rates of change of constant things is 0. So like we saw, the partial derivative of t with respect to y was just 0. That t is missing right there. There's 0 right there. So partial derivatives is just a derivative. Assume all other variables are constants aside from the one with which you are taking the derivative with respect to, which in our case will always be y. So what this is saying to us is this. Again, our simpler version. There can only be one solution to an initial value problem as long as our differential equation function and its partial derivative with respect to y are both continuous. Graphically, this is the important part. This is like the biggest thing that we're going to get that's going to carry with us all semester, the very, very meaningful part. Particular solutions cannot intersect one another where f of ty and the partial derivative of f of y are continuous. We can't get intersections. This is saying they can't cross each other, right? That can't be the case because then there wouldn't be uniqueness for that initial value problem. There would be two different solutions otherwise. We're thinking of solutions graphically here. So I think the graphical intuition or takeaway from this right here is the most meaningful part to know. And this is something that we saw in our last video, is that we are now stating if we guarantee that this is continuous and this is continuous, you will never have any two solution curves that cross each other. And that's very, very powerful for us here. So let's look at an example of seeing this happening right here. Right? So in this one, I intentionally stated nothing but a differential equation here. We kind of just want to like talk about this guy, right? So since we just talked about existence and uniqueness, we just talked about wanting to know that f of ty and the partial of f with respect to y are both continuous. So here I can see 3y to the 2/3 is continuous. Right? That's a continuous function right there because I can take the, notice, and this is continuous, like 0 to the 2/3 is still going to be 0. We can do negatives because that's an odd fractional power, not an even fractional power. So this is continuous over the real numbers here. We can take its partial derivative here. So we're calling this thing, this is our f of yt. So I'm going to take my partial of f with respect to y. And what do we get? Well, the 2/3 pops down, and we subtract 1 from the power. Notice, very importantly, this is not continuous at y equals 0. So we are unsure about uniqueness of solutions at y equals 0. All right. So we don't meet the criteria for the uniqueness theorem with this differential equation right here because the partial derivative of f with respect to y is not continuous at y equals 0. Therefore, we are not sure at y equals 0 if we have uniqueness of solutions at that location. So now that we've kind of thought about how this problem relates to, how this differential equation relates to the uniqueness theorem, let's go ahead and actually solve it. And let's see if we can kind of think about the things that are going to kind of pop out from this guy right here. So let's do the thing here. So dy dt equals 3y to the 2/3. It is separable because it's autonomous. So let's make this y to the negative 2/3 dy on the left. And we can make this a 3 dt on the right? All I did was just move over the y to the 2/3, hit it with an integral on both sides. I'm going to go ahead and add 1 to the power here, so this will become a y to the 1/3. I know if I were to take the derivative of y to the 1/3, a 1/3 would pop down. I don't want that, so I'm going to introduce a 3 right there to counteract that. This should be equal to 3t plus c on the other side over here. I don't care about c being kind of remaining officially appropriate here, so I'm just going to divide everything by 3 and just get y equals t plus c. And then I'm going to go ahead and y to the 1/3 equals t plus c. And this is going to take me to y equals t plus c cubed. Right? So let's consider what's going on at y equals 0 now. Right? So let's go ahead and consider the initial condition of y of 0 equals 0. Right? If I do this, then I'm going to get 0 equals 0 plus c cubed. And so it looks like c is just 0. So it looks like our particular solution is just y equals t cubed. That passes through 0, 0. But now I'm going to say to you, just stare at this differential equation for a second and tell me what easier solution you see. Well, the solution that I see, the easiest possible thing I can think of is y equals 0 makes this equation true. 0 to the 2/3 is 0, times 3 is 0, derivative of 0 is 0. So what I know is that there are really two different solutions that pass through the origin here. So it seems like we get both a cubic and we get the horizontal y equals 0 solution as well, right? Two solutions that both pass through t cubed and y equals 0. So here, we did not get uniqueness of solutions at 0, 0, and in fact, there were two. We had two solutions that intersected at 0. So now you should be asking yourself, if your initial condition is 0, 0, how do you know which of these two trajectories you would follow? Good question. And there will be a very good homework question associated with that for this week 2 content right here that we're going to discuss as well. A little bit of a written thing. This is certainly more of a thinking question right here. And so we're going to apply a sort of a real world scenario that's going to have this behavior right here. And thinking about the real world scenario will help to influence your answers to that question. If you were to start at 0, 0, how do you know which of these two trajectories you would end up following? And that's a big issue for us. So again, it's really, really useful to us to know that that can't happen in lots of situations. So if we can establish that the conditions for the uniqueness theorem are met, it's really useful for me to know in trying to get a graph of all my general solutions. I want to know that that can't happen, right? In this situation, it could happen, and it did happen, that we had a non-unique solution at y equals 0, because at exactly y equals 0 is where our partial derivative with respect to y was not continuous there, right? And that was the one place where where we failed to have uniqueness, was exactly at that one location right there. So again, knowing when that can't happen, really useful to us, because then we know that all of our solutions are going to never touch one another. That's a really nice thing to know for helping plot the solutions when we plot our solution curves when we can't actually solve the differential equation out there. Right? So again, we will get a question that's very strongly related to this. Well, then what does happen at 0, 0 that you guys will do a little bit of written stuff for this week here. Right? So there's our example of the uniqueness theorem failing at a point, and what happens graphically when the uniqueness theorem fails is we get some ambiguity. You don't really know where you'd go from 0, 0. And again, that's sort of introducing some problems for our attempt to suggest that this is mimicking a real world scenario right here. So now let's see what happens when the uniqueness theorem does work out and that we get the things that we want. And I'm immediately seeing that I chopped off the end of my equation right there. Wow, I don't know how I spotted that one. Okay, so let's consider this initial value problem here. Let's look at a little bit of a grosser example. dy dt equals 1/2 times y squared minus 4 times sine squared of y cubed plus cosine of y minus 2. So immediately, I am hoping that you're saying to yourself, yep, it's separable. Nope, I can't do it because there's no way that you are going to be able to integrate 1 over this expression right here. No way. So I know that we're never going to solve this equation. It's not like we're not going to do it. Probably nobody's going to do it. And even if I could give you the y equals equation that was the solution for this, would you even be able to interpret anything meaningful about that equation? Would you be able to graph it? Would you be able to tell me about limits that are associated with it? Probably not. So it doesn't even matter if you could even write down an explicit closed form solution for this. As far as I'm concerned, it's obviously going to be so hairy and disgusting, I could never make heads or tails of what's actually going on with it. But despite that, I still want to be able to discuss things like long-term behavior of a particular solution. So I'm saying here, if we know that we start at the y value of 1/2, what I want to know is what will happen to our y value as time tends off towards infinity just using this differential equation right here. And again, we're just skipping over getting the solution and just attempting to interpret long-term behavior without ever having seen what y equals actually is. Right? That's the kind of the big important thing that we're getting out of this guy right here. So when I look at this differential equation, there's obviously a gross part and there's obviously a clean part that's associated with this guy right here. And so one of the things that I see right away right here is that if dy dt equals 0, what that says to me is either y squared minus 4 is equal to 0 or sine squared of y cubed plus cosine of y minus 2 is equal to 0. Those are the two ways I'm going to get roots out of this thing. This is where, oh, sorry, I should have written my important word here, equilibria. Where is there no motion? Where is nothing happening? Where is dy dt equal to 0? That's a good place for us to look for some straight line solutions. What we now know is that some of our straight line solutions are going to be pretty helpful for us because if we have existence and uniqueness, then no other solutions can cross those. And that's pretty valuable. Right? So where are my equilibria? Well, I can clearly see here that we're going to get plus or minus 2 from that one right there. I don't think I need to show the algebra. I think you guys are on board with that one. Also notice over here that sine and cosine can take on individually, they can be as extreme as +1 or -1. Notice that they're fighting against this -2. So the only way we would get a root here is if there was some value of y that caused both sine squared of y cubed to be equal to 1 at the same time that cosine of y is equal to 1. This is a little bit harder to actually algebraically show, but I hope that you're reasonably convinced and you can absolutely go look at a Desmos graph and find out that there are no places where this is going to be equal to 0 here. This is always a negative quantity. Right? This expression right here, that -2, it's always going to overwhelm even the largest positive amounts that these could ever collectively have at the same time right there. Sine and cosine just don't reach maximums at the same time. We would need them to both be their maximum value of 1 simultaneously to get to 0 right there. Since sine and cosine are never maxes at the same time, this is always going to be those sine and cosine are less than 1, or collectively they're less than 2, I should say. And so when we subtract off 2, we're always going to get a negative contribution from that component that's right there. So one thing that I know is that if I were to, man, I didn't give myself enough room for any of this stuff here today. So what I know is that I could go ahead and kind of start graphing some things right here. I know that there is one solution down here at y equals -2. There is one solution up here at y equals +2. This is my y equals 2 and my y equals -2. This is our initial condition, right? There's the height of 1. Our initial condition that was given to us was the height of 1/2, right? Y of 0 equals 1. That's my initial condition right here. Remember that our question is, what's going to happen in the long term to any solution that passes through that initial condition right there? One of the really nice things is that by identifying these two equilibria solutions, just the letter y, just the number y equals 2, and remember the y equals 2 works because plugging in 2 makes the entire right hand side equal, and the derivative of 2 is going to be 0. So we get 0 and 0 right there. So these two straight line horizontal solutions are solutions to the differential equation right there. And what we're kind of seeing now is potentially they are going to be bounding solutions, right? Do we have existence in uniqueness? And I'm going to go ahead and very generically here say yes. What you can see is that we have polynomial components times trig components. This is something that is defined everywhere times something that is defined everywhere. And so its product will also be defined everywhere, right? So this is continuous everywhere. So I'm going to say yes, f of ty is continuous everywhere. Product of two continuous functions is going to be continuous over at least their smallest subdomain. Both these are continuous over the whole real numbers, so their product is going to be. And I should say that was for existence. For uniqueness, I'm also going to kind of generically right now say yes. I'm not going to take that derivative right there, but if we're taking the derivative of a function that is defined everywhere, and we know that the derivatives of quadratics are linear, derivatives of sine squared and of cosine are also defined everywhere because we're just going to get back more sine stuff and more cosine stuff. We're still just going to have a big old product of polynomial times trig stuff. So we're going to get yes again, right? So I'm going to say partial f partial y is continuous everywhere as well. So the reason why this is important is that this means to me that no solutions can cross the two horizontal solutions. So again, by knowing existence and uniqueness, what that guarantees me is whatever the curve is that's going to pass through our initial condition, it can never cross any other solutions on the entire plane out here. Since I have found two horizontal solutions, I am guaranteed that our solution is bounded between -2 and 2 for all time. So I haven't answered our question yet, what's going to happen with this limit, but I have at least made a pretty good statement already. I can already say I am guaranteed that given the initial condition of y anywhere between -2 and 2, it will remain between -2 and 2 for all time. So for all y contained in -2 to 2, the solution through 0y will remain within -2 to 2 for all time. Yeah, Naraku, good to have you here. So we get this boundedness specifically from our existence and uniqueness theorems, right? So existence and uniqueness kind of lame because they don't actually give us a solution, but they do tell us, they guarantee us behavior of other solutions if we can find some simple bounding solutions to help us out. Now, here's some other things that we can do. I said I wanted to know the value of the limit straight up, not just in what region does it live in, but literally what's the value of the limit as time goes off to infinity right here. And here's some other things that I can see for myself now. Another thing I can see for myself is that in y being from negative 2 to 2, the expression y squared minus 4 is less than 0, always. So we're guaranteed to get a negative contribution from that guy. Another thing that I can see is that in y being an element of, in fact, the real numbers, our sine squared of y cubed plus cosine of y minus 2 is always less than 0. And that's for all real numbers out there. So what that says to me then is that dy dt is less than, or excuse me, that should be a greater than because we're multiplying. Here's what I should write. This is equal to then 1/2 times a negative times a negative. So I'm guaranteed then that dy dt is always positive, at least in our more restricted domain right there. For all y between negative 2 and 2. Right? So this is just me doing a little bit of algebra right here. This is me saying, is our function going to grow or is it going to decay when we start from this initial condition of 0, 1/2 right here? What I just determined is that the two contributing factors here, that factor, the quadratic factor, guaranteed to be negative always whenever y is between negative 2 and 2. The trig factor is guaranteed to be negative actually always for literally any y value. That's always going to be negative because sine and cosine will never be maximums at the same time right there. So in this interval between y being negative 2 and positive 2, this entire expression is guaranteed to always be a negative number times a negative number, always giving a positive number, meaning dy dt is always positive for all y's in the interval from negative 2 to 2. And so what that says to me now is I can conclude that whatever our solution looks like, I don't know the shape of the curve, but I know that it is going to grow forever, but also be bounded above by y equals 2. And consequently, I can conclude that the limit as t goes to infinity of the particular solution going through this initial condition, guaranteed is going to be 2 in the long run, because it's going to increase forever, but it's also bounded above by 2. And in Calc 2, you learned the bounded monotone theorem right there, right? Maybe I should say that. So I'll say here, since this solution is bounded above by 2 and always increasing, we're guaranteed to be limiting towards 2. It's going to increase forever, but it's never going to get to 2 or above right there. So it's going to limit towards 2 in the long run. So our monotonic bounded theorem. Pretty cool. Pretty cool. So again, I've said this like 12 times already, and we're just barely even getting the semester started still. The whole point of this class is that so many useful differential equations you can't solve for the equation that is the solution. But that doesn't mean that you can't find some easy solutions that aren't the ones that you necessarily care about, like our equilibrium solutions here, and use them to give you lots of really valuable information about what your solution of interest is actually going to behave like. I know for a fact what the long-term behavior is of my particular solution of interest is, just by knowing that it's bounded by things and knowing that it's always increasing right there, right? Ultimately, this is a bunch of like Calc 1 and algebra that we did right here to determine this, because we literally couldn't do the calculus. This is separable, but if you divided that stuff over and attempted to integrate, I'm hoping you're laughing at yourself like I'd be laughing at you in that situation right there. We just can't perform the integration so often. That doesn't mean that we can't describe exactly what the behavior of our solutions is going to be like. Now, again, I don't know what this looks like. Maybe it's concave up, maybe it's concave down. I don't quite know what the shape of the trajectory is, but I know what its long-term behavior is going to be out there. So I think that we can kind of conclude that I know that this guy is going to have to do something like this. Right? I know for a fact that that's what its generic shape is going to look like from that initial condition moving off towards positive infinity time. Pretty cool. So this theorem is very, very helpful. And so our big takeaway now is you should say, dang, equilibria solutions, super useful. Even if they're not the ones that are of interest to you, even if they're not related to your initial condition, they will place serious boundaries on where other solutions might be able to live. So when you end up in the situation that you want to know about a solution that you can't get your hands on, you can at least know what it's bounded by. And that's giving you a good description of the long-term behavior of your solution of interest. Right? I think that's kind of what my final claim is right here. So the awesome power of the existence and uniqueness theorem is that it allows us to use, and I put in parentheses there, are easy to find solutions to place boundaries on other solutions. So knowing that you have one solution bounds all the rest of them. That's really valuable for us. Now, even better than that, later this semester, we're going to see solutions that are things like circles. Well, that's an epic boundary line right there, because that means that any solution that starts inside of it is going to have to remain inside of it forever. And solutions that start outside of the circle are going to have to be outside the circle forever. That's some great boundedness concepts right there. So this ends up being something that is heavily used in lots of other major claims that we want to make about long-term behavior of systems of differential equations once we get into our system stuff out there. This doesn't go away out here. So existence and uniqueness, real powerful because it allows us to bound solutions that even if we can't find them, we know where they live now. So let's look at there's technically two examples left, but the second one is very closely related to the first right here. So let's think about some claims that we can now make based on existence and uniqueness theorems right here. All right. So consider dy dt equals 1 plus t squared over 1 plus y squared. And the first thing that I want to ask you is, what's the easiest solution that you can see by visual inspection? Don't go doing math. Make some educated, simple guesses and see if it works out. If you're watching this not live, then you should pause right now and stare at this thing with some squinty eyes and say, what could I define y to be to make this a true equation without really doing any major math computations out there? Now that you've unpaused your video, I'm going to look at this guy and I'm going to say to myself, man, this numerator and denominator look very closely related to each other. Notice that if y is equal to t, hold on, let me get back in the consistent coloration here. And if y is equal to t, then I'm going to just straight up get 1 is all that we have on the right-hand side, and the derivative of t is also 1. Hey, thanks, Naraku. Cool that you're checking this guy out right here. Hopefully it's flooding back your memories here. Right? So y equals t is going to give me the derivative of t is 1 is equal to 1 plus t squared over 1 plus t squared right there. Get rid of my errant parenthesis right here. Cool. So that is a solution that works. And now I'm also saying, I don't know, what initial condition is going to be nice and convenient with this one? Looks like 0, 0. All right. So what I'm saying to you is, I haven't solved the general solution for this. I really don't know. It looks like it'd be really gross because I would have to multiply our 1 plus y squared up to the left-hand side over here. Integrate both sides. It looks like we're going to get a cubic in y equal to a cubic in t. So you'd need to be able to solve a cubic in y for some t stuff. It's going to be nasty. I don't screw around with ever trying to even do algebra with cubics. That's good enough for computers for me. I handle quadratics and down, not much. But yeah, the point is maybe you could do it. But even if you could, would you even be able to work with the equation that you'd get with for y? And the answer is kind of probably not no. So what I'm thinking is this. I don't know what the overall graph looks like of all of my possible solutions that are out there, But I do know that if you're thinking about the initial condition 0, 0, I do know that I'm going to get the solution y equals t passing through it. And what an awesome bounding solution this is right here. And by the way, we do have a continuous derivative as long as y is not equal to -1. So it looks like that's a point of concern here, but we're not going to deal with the point y equals -1. So it's continuous everywhere but there. And when we take our derivative, we're going to get that same feature that everything but y equals -1, it seems like we're guaranteed existence and uniqueness. But that's not really my point of concern right there. We are guaranteed existence and uniqueness for our other locations aside from that one right there. So the point is, this is an awesome first solution to find because it just chopped our entire plane in half. So now suppose we consider the initial condition that's located at -1/2. What can we say about this solution? Well, there's one solution that I know. We're now interested in this other particular solution that exists at -1/2. Well, what I know now, because of my existence and uniqueness, that we are good with our existence and uniqueness at points like 0, 0 and at 0, -1/2, that this can't be crossing anywhere else, right? And so what I know is that this solution, y2, if I call this my y1 of t, is that it cannot cross this, right? So we might be able to find some other solution that's out there maybe, but the point is, whatever it looks like, this y2 of t, it must be the case that y2 of t is less than y1 of t for all t, right? So again, even if we're not solving things, even if they technically were solvable, it's still giving us this huge information. You're saying, oh, hey, I found a solution. Can you tell me anything about it? Yep, I for sure know it's less than what we found for our first solution because this one's chopping our plane diagonally in half right there. Let's look at our last example. It's going to kind of build off of this one, but I'm going to kind of make it much more generic here. Might as well just bump this guy down. So, example. The class is presented with an initial value problem with dy dt equals f of ty and the initial condition y of 0 equals 0. And it has a particular solution of y equals t and satisfies the existence and uniqueness theorems. Right? So, what I'm saying to you is that I'm saying this y equals t is in a sense coming from that previous example, but I'm like making this more generic now. I'm not saying that that was that particular differential equation. I'm just saying it's some differential equation. It has that solution y equals t passing through 0, 0 right there, right? And it satisfies the existence and uniqueness, right? So here's what we want to do. 3 students make claims. Alice claims to have found a linear solution with y of 0 equal to -1/2. Bob claims to have found a quadratic solution passing through y equals -1/2. Carol claims to have found an exponential solution passing through -1/2. What do you think about these? Are any of these people right? Are all of them right? If they are right, what do you know about the solution that they found? Here's some things that I think that I can say. Let's talk about Alice. In fact, hang on, before I start this guy right here, I want to kind of generically graph this guy. I guess I could, well, yeah, sure. Okay, all right, I'll just do it like this. We'll draw a separate graph for each of them. So in all the cases, this is a known solution, that y equals t equation, right? We're considering this initial condition that y equals -1/2. And so our question is, Alice claims to have found a linear solution that passes through y equals y of 0 equals -1/2. Well, if she found a linear solution, is it possible? That's my first question to you. And I think that it is. Now, what we know by the existence of uniqueness is you are not allowed to touch the line y equals t. So what must be the case? It must be that she found y equals t minus 1/2. Any other slope would cause intersection of solutions. So if she's saying I found a linear one, I know the one linear function that she could have possibly found, because literally any function with any other slope would eventually end up hitting the particular solution that we already know about that goes through 0, 0. Since the existence and uniqueness theorems have been satisfied according to the problem here, it couldn't have happened that those are going to intersect. And so it must be the case that she found y equals t minus 1/2. It has to go through the point 0, -1. So that also restricts down to my y-intercept to being that only one right there. So this says to me there's only one possible linear solution that could possibly cross through there, again, not knowing any information about this differential equation otherwise right there. So Alice could have potentially been correct as long as that's the one that she found. Okay, so I'm realizing now I kind of well I'm like looking at my notes for this problem right here, and the thing that I'm recognizing is that I maybe did not like genericize this problem the last time I did it, and maybe this is like holding over that f of ty from our previous example right here. Maybe we'll just talk about both cases, or I think we're still making the same types of claims right here. So Bob is claiming that he found a quadratic that's going through this, but we know that our solutions are bounded by this guy right here. Right? So it seems to me like we could make some more general statements now. One thing that I know is that if there's a quadratic that goes through this, it must be an opening down quadratic. It's not possible for Bob's quadratic to be opening up to have a positive coefficient on the t squared term right there, because then it would intersect our solutions. I also know that even if this thing opens down, it could open down and be like super duper wide, in which case it might hit that linear equation as well. I know that linear or quadratic equations get wide by having very, very small a values, like ax squared, right? So it seems like there's probably some restriction on a that we could determine here to prevent that parabola from being too wide to the point where it intersects that thing right there. So it seems to me generically plausible that there could be a quadratic right here. Um, However, another thing that I'm seeing, by the way, is so, and again, I'm kind of like mixing two problems right now. If we're just generically stating any old f of ty, then I think that we can say, yeah, it's possible, but it's got to open down and not be too wide. If we were in fact referencing this particular differential equation as being the one of interest, you should notice that the numerator is always positive, denominator is always positive, meaning the slope of our solution should always be positive, and that's never going to be true for a quadratic, right? Quadratics always spend half their time sloping downwards. So if we're referencing the particular, so maybe I'm gonna write this stuff. Um, if we had f of ty equals the, was it our 1 plus t squared over 1 plus y squared, always positive. So for this function, we couldn't possibly ever have a quadratic solution. Open up it would touch, open down would sort of be okay, except it's got negative slopes. And our function here says slope is always positive, always increasing, because we got squared stuff divided by squared stuff. So if we were referencing our previous examples function, then there just straight up couldn't be a quadratic. If we're referencing a more general f of ty, then there's at least some restrictions that we could place on what the quadratic would be. Finally, we got Carol. Carol's claiming to have found an exponential solution. Again, got ourselves a nice linear solution, already known, going through 0, 0. Right, there's our y equals t once again. Could there be an exponential solution that passes through 0, negative 1? And it looks like now the answer is probably yes, right? It looks like I could fit an exponential through here. Now, it can't be some exponential that does our traditional like exponential decay or growth like this, because any exponential will eventually grow faster than linear, whether it's growth or decay. But maybe I could sort of like do, one of these guys right there. So it looks like for y equals a e to the kt, we must have both. Well, I guess a equals negative zero point 0.5 and k needs to be less than 0. We've got that negative initial condition, and we should be having that decaying exponential rather than a growing exponential right there. So both of those guys being negatives, that we get our bowed down exponential equation right there. So it seems like Carol's is, in a sense, maybe the most plausible of our possibles right here. For the generic or for the particular case like I wrote up in purple right there. So again, it's good for us to stop and think about how much restriction do we get just by knowing one line that crosses your plane. Now you can go down the list of your entire family, all the families of functions that you know, and say, could I get a solution of this form? Could I get a solution of this form? Could I get a solution of this form? If we think that we know that this might work out, then maybe now you just go ahead and plug in that y equals equation into your differential equation and solve for the parameters of a and k that make it work out. So again, this is like kind of a part of our guess and check, like advanced guess and check strategies right here. It's saying know your limitations and know the possibilities that are still out there given the limitations that you have. But when I say limitations, I feel like that sounds negative when really I mean, oh, thank goodness we have one solution bounding our plane so it restricts all the infinite possibilities down to a much smaller category of overall possibilities that are out there. Right? So for existence and uniqueness out here, super important. This says to us, as long as we have existence and uniqueness, we know that our particular solutions won't cross one another. And what that means to me is that we can make great restrictions on all the possibilities that are out there, taking us from an infinite world of possibilities down to a small number of possible things. And again, as I just kind of said, this is now kind of leading us towards a potential guess and check type situation. Now I'm saying, I don't know, looks like an exponential might be good. Let's plug in y equals a to the kt and see if we can get something to pop out that's going to make that guy happen right there. And maybe it will, maybe it won't, maybe it will, but you just couldn't solve for it. But still, it's a guiding thing right there. So existence and uniqueness is very powerful. I would think that the best thing for you to do is to interpret it graphically, like we've been thinking about right here. This should be emphasizing to you that identifying equilibrium solutions is a super valuable thing for us to be able to do, because if we know when we experience a horizontal solution, that immediately chops a chunk of our plane off. So if any solution starts below it, it stays below it. If any solution starts above it, it stays above it. Heck, getting multiple equilibrium solutions, now everything's bounded within, everything that starts between two of them remains between the two of them for all time. So existence and uniqueness is going to tell you, where do your solutions live? Even if you can't find them, you know what neighborhood they're in now. And that, while that's kind of in a sense still dissatisfying that we don't know where they are, pinning things down from like the whole globe to one neighborhood, massively useful for us in helping us make better guesses and still being able to answer questions of interest like understanding long-term behavior and stuff like this. So really powerful stuff, this existence and uniqueness. It's going to follow us the entire semester here. We're going to say, since we have uniqueness and solutions, we know blah, blah, blah. Like that's going to come up in our arguments quite a bit here. So nothing too complicated with using it. All you have to be able to do is verify continuity of a function and continuity of the derivative of a function. And even this idea, even if you haven't seen a partial derivative before, it's not too big of a stretch. Treat everything as a constant except for y. That's all we're doing with our partial derivative right there. So applying this is pretty easy. Using this, vastly important right here. So this is one of the reasons why it's one of the earliest sections in the book. It's really important for us. Where we're going to pick up next week is in section 1.6. We're going to get equilibria and phase lines. We're going to talk about more about the importance of these equilibria, and we're going to see that those slope fields that we drew in our last video, that we can do way better than our slope fields. We can do a lot less work and get almost a more meaningful or easier to interpret graph from it, which is really, really valuable to us. Then in section 1.7, also next week, we are going to see our solutions to our linear differential equations. So in section 1.7, for those of you that enjoy your equation solving a little bit more than just our broader conceptualization that we've been doing here, we will get our second analytic technique should be in section 1.7 for linear rather than separable differential equations there. So we will also be getting in this week 2, we'll be getting our first written homework assignment. The written homework assignment will include, it's not going to be too long. I want the written homework to be good rather than a lot. It's a quality over quantity kind of thing for the handwritten homework. And this one's going to be, in a sense, a little special in that we've really been doing a lot of conceptual things. And so there will be some good sort of like a little bit of like writing that you're actually going to end up doing for this one, as opposed to more like doing math more directly right there. So that's all I've got for you guys for section 1.5. That's our second topic here for week 2, and we'll be picking up week 3 with 1.6 and 1.7. Remember, the only real like out of order stuff that we're doing this semester is I'm just plucking out all of the numerical sections, the programming sections. I'm separating those out from everything so we can do that in one tight unit rather than like do some programming, stop for a while, do some programming, stop for a while. Since we're not all programmers, since we're not sitting in a classroom where everybody has their computer out in front of me, it's going to be a lot easier if we collect that into one nice little unit right there. So that's kind of our only major alteration to the route through this textbook is skipping 1.4 and 2.4 until we're ready for them out there. Cool. Happy week 2. And I will see you guys for phase lines and for linear differential equations in week 3. Come hit me up in office hours if you guys got questions, want to go over anything. I'll help verify your homework, stuff like that with you guys. See you guys there.